Hello community! I was asked by a class if I can explain how AI agents learn between themselves. What if we have more than one AI agent? How is it possible that they can learn? Hello class, welcome. I make it as easy as possible. So, an agent here in the context of AI is an entity that perceives its environment through its sensors and acts upon it to achieve a specific goal. Now, a multi-agent system is now an extension in this definition where we have multiple agents interacting with a shared environment. But this interaction can be cooperative, it can be competitive, or it's just neutral and each agent ignores the other agent. And we have this in robotics, traffic management, automated trading, or complex decision making, and more. Now, we do have an optimization problem in math because we can have conflicting goals. So agent may have goals that conflict or interfere with each other. Or maybe there is just not enough resources for all the agents. Or we have limited information. Each agent typically has only a partial information about its real close environment and is not able to see where other agents are acting and what they need on resources. So this can complicate our decision-making process of a bunch of agents. And of course, we have to compute of all this, so it can increase here the complexity of the coordination and the communication here simply on a code base. Now, if we do now the optimization in math, we have to define what kind we want. What we are focusing today is the best decision for each agent while considering the overall system performance. So AI, technology, enable here the multiple agents to learn from their environment and improve their decision making over time. And we have one algorithm, and this is reinforcement learning. We use this for, 5 years already to have here this optimization step in the behavior of our agents. So reinforcement learning as a method where agents learn to make decisions by receiving rewards or penalties based on their action. A simple principle. Now, if we have multi-agent reinforcement learning, it's not so simple anymore because, we have here, for example, cooperation via a reward shaping, and this is what we're going to look at. So you modify the reward structure and the reward functionality, the function, to encourage agent to cooperate more. For instance, incorporating the success of neighboring agents within your defined environment into an individual agent reward calculation can now promote and enforce here a more collaborative behavior, so that the team achieves its goal and not just one agent achieves its goal and all the other agents fail. So we have, of course, challenges here, such as credit assignment, so determining the contribution of each agent to the overall outcome. What is the most important agent? How many agents do have to work together that we can find a solution? And everything that it is in a dynamic environment and non-stationary environment, where the behavior of the agent changes as the learning progresses. Now, first thing to do, this in code, we try to reduce the complexity. So we go from, a 512-dimensional vector space or an operational space, we try to bring it down to low dimension, let's say to a 2-dimensional floor. So in order to evaluate here the agent's influence on its neighbor, we can integrate this interaction into the reward function, promoting here the cooperation, and we do this here on a particular type we call multi-agent pathfinding. And you understand immediately why if I show you that in 2 dimensions, this is just here a floor. Let's say we're in a warehouse and we have robots. Let's say this is an Amazon warehouse and the robots just pick up here the different goods from the different aisles. Therefore, we have multiple agents. They must find their path in a 2-dimensional manifold from their start location to their respective multiple destination locations on a shared graph or on a grid structure if they are allowed just to move on a particular grid, while avoiding at least collision and maybe supporting each other. Because imagine in one aisle, there's just enough energy that is provided for 3 agents to be active there. So if more than 3 agents or 4 agents want to enter now this hallway, they have to wait till this energy bottleneck will be resolved. So you need an intelligence for an optimization problem on a 2-dimensional floor, and this is interesting. Now, in general, let me tell you that we have 2 types here that we can change this, or we can control it. At first, we have a central brain. We have a centralized planning. You have an agent. This is the mastermind in the middle of all the agent networks, like in my last video. But this centralized planning, this needs to be the most intelligent agent. This agent needs to understand all the other functionality of all the other set of agents operating in the complete ecosystem. So this can be really computational intensive, but it has the advantage. Maybe you can position it somewhere where we have here no problem with electricity to provide electricity to the central agent. Maybe it is somewhere in a box mounted here at the wall, and it has not to be flexible and dynamic, interacting with its environment, but it's focused here only on the planning task. However, if you want to be mobile, if you want to be interactive, if you want to be a little Speedy Gonzales who is everywhere, then we have to go for a decentralized approach. Now, this can be a little bit problematic because now you have to self-coordinate here all the agents. So we have to put something in the intelligence of each little single agent that they understand that they have to communicate with the other agent, and there's a goal that is higher than just their singular simple goal. So you see, it gets interesting here. Now, you know, of course, the way we do it in a classical way is independent Q learning. So we have a reinforcement learning algorithm where each agent independently learns its policy using here Q learning. This is a traditional path. And then in IQL interact, we have now agents that learn from the value of state action pairs, you remember my last video, through interaction with the environment, aiming now to maximize, and now not a single reward, but a cumulative reward function. So this is now a very simple, straightforward way how we try to solve here an optimization for Q learning. Now, the Q learning here for our bunch or set of, I don't know, a dozen little agents, this is not so easy. Each agent treats other agent now as a part of the environment and learns without explicit coordination. And this fails something because you can imagine this. If you have a dozen of little robots and they have no real coordination function and they just see each other as a part of their environment that they react with, there's not a perfect coordination happening, and we have a suboptimal performance in a cooperative task like the multi-agent pathfinding if you have 12 little Amazon robots on the floor. So therefore, you immediately understand what we have to do. We have to make those little agents able to communicate with each other. So they understand exactly where are the other agents, what is their task, what is their progress, how do we need resources, how do we have to act together to reach our common goal. Now, there's a specific method that's called reward shaping. The influence measurement is easy. It evaluates how an agent action impacts its neighborhood of other defined, let's say, 11 agents. So this involves assessing the potential, and this means the positive or the negative effects of an agent path choices. Remember, we are just here on a 2-dimensional grid. We are not in a decision-making 512-dimensional feature space. We are just 2-dimensional. And here the effects of the agent path choices on the other agents in the vicinity. So we modify now this simple reward function to include here this other matrix. So an agent might receive here additional rewards for action that help its neighbor reach their goals faster or more safely. So we're not optimizing for a single agent, but we are optimizing for the common effort of a group of agents. Now, this is now something nice when you immediately understand it, it's called distributed learning. So you remember each agent learned independently its policy using here the modified reward function. And despite here the decentralized nature of this learning, the cooperative reward structure that we put in now this formula, it helps to align now the agent objectives, leading here to an emergent cooperative behavior. And now you might ask how we do this. What is the mathematical formula and how we code this? Now, if we use now reward shaping, and I'll show you the publications for this in a minute, there are some steps we have to take care of. Remember, the state representation. So, including the neighbor's agent positions and the goal are now in the state representation. Then, as you know, we have to calculate the rewards. So we add now terms to the reward function that reflect now the benefits or the cost or the energy or whatever you want, the time, of an agent actions on others. And there is a beautiful complexity hidden here. And then we have a policy update in a typical reinforcement learning. Update the Q values based on these adjusted rewards, which implicitly, you remember, we added now a term to encourage now cooperation between our bunch of little AI agents. If you're not really sure about Q learning and Q functions, I have here a video where I go from A star to Q learning and from Q learning to Q star. So if you're not sure, maybe have a look here in 55 minutes. I explain here the complete development here for AI reasoning. Now this Q function, Q state and action definition, defines now the total reward an agent can expect by starting at a state S, taking a specific action A out of a set of different actions, and follow the optimal policy thereafter. Now, easy, you know that a multi-agent Q learning with this beautiful abbreviation where each agent independently learns its own Q function based on joint action of all agents, and the Q values for each agent is now a function not only of its own state and its own action, but also potentially of the state and action of the other agents that are within the communication reach, that are within a specific environment that is important, that the agent knows, hey, I have my little other agents here in a certain distance, and we have to take care that we together we reach our goal faster. Now, multi-Q learning is something beautiful, but it has a complication. Why? In a multi-agent setting, the action space, like I showed you in my video, becomes now the product of all the possible action spaces of all the other agents, leading now to a rapid increase in the complexity of the Q function. And 4 or 5 agent is no problem, but if you go to multiple agent and multiple set of agents, this can become real complex real fast. So unfortunately, currently we have a significant increase in the computational complexity. The role of the communication in multi-agent Q learning, where agents might share their states and their possible actions, or even the Q value to better assign the policy, this is all now becoming real complex. Plus, we have the question, hey, does this all converge to an optimal policy for the set of all my agents? So how can we guarantee here a convergence in the multi-agent setting to our common goal? And this is really challenging if you want to compute this and if you want to make sure right from the beginning that you have the right boundary conditions on your equations. Great. So let's come now to a new idea that I want to present to you. And this was just published 3 days ago. So it's a real research paper. And there's now a unique reward shaping technique based now on this independent Q learning, IQL. And the aim of this new method, which the author called now a cooperative reward shaping, is now to evaluate the influence of one agent on all its specific defined neighbors and integrate such an interaction into the reward function, leading now to an active cooperation amongst those agents in our epsilon environment, where we understand that we have agents that should work together, or they have a common energy resource or a common energy buffer. This cooperative reward shaping is now a method specifically designed to address the need for an enhanced cooperation in a multi-agent setting, particular when we have the agents that are learning now through our beautiful Q learning methodology. Now, as you guessed it, Course modifies now the traditional reward mechanism by incorporating additional rewards that account for the positive impacts an agent's actions have on other agents in its epsilon environment. Beautiful. Now, a little bit of mathematics. You remember from my video here the mathematical code implementation here of the Q learning algorithm. Very simple, very easy, no problem at all. Then the mathematical formulation of the Cooperative Reward Shaping course in Q learning. And then if we put it together, this is our simple formula. Good. Now let's do this. Let's have here a look now at this new publication, mid of July 2024, Cooperative Reward Shaping for Multi-Agent Pathfinding. And you see this is done here on the simplest case, a two-dimensional manifold or a two-dimensional sphere, where our robots move. Since there was no affiliation of the authors, I looked up at Google Scholar here, our lead scientist, and we see here, okay, Zhejiang University, China. Interesting, if you look here, the other publication here, for example, if you ask yourself, why are we investigating this? We know how a Tesla car drives. Yeah, but you know what? Just have to look at the title, for example. An end-to-end multi-sensor fusion method based on deep reinforcement learning in URSNs. And you think, okay, this here is an Amazon warehouse, the floor, two-dimensional, no problems at all. But if you look here at an underwater acoustic sensor network, for example, if you have a submarine that dives down on a continent shelf, or a submarine that climbs up a continental shelf, and you have multiple underwater sensors, and you have to bring them together to fuse them and provide a three-dimensional pathway, let's say, to the surface, then you immediately understand what we are talking about. Or if you think this is underwater, think about you are moving now in a particular medium, let's say air, and you go ultrasonic. You want to have here the perfect pathfinding now for a three-dimensional path if you have a particular target. So you get the idea what we are doing here. Now, the authors here have a very particular idea. They build upon something, and they build upon something that is called the DHC. And I will show you this in a minute. So you see, this course new framework just becomes a little module you attach here, and it does here a specific thing here to a methodology that we know, that we apply already here for our applications, whatever it is, underwater or supersonic. And this is now a step forward. So combined framework, of course, in DHC algorithms, just to tell you, if you find something like this and you don't know what is it, it is easy. You just go back and you have a look at references to understand. And now for multi-agent pathfinding, you can imagine that this particular application, this is researched for years and years. And I have here 3 publications if you want to have a little bit of a deep dive. I think you should read here those 3 publications. First one is from December 2021, Learning Selective Communication for Multiple Agent Pathfinding. Then Stable and Efficient Shapely Value-Based Reward Reallocation for Multi-Agent Reinforcement Learning of Autonomous Vehicles. And maybe we are not only here in a 2-dimensional space, but maybe already in a 3-dimensional space. This is from 2022, and then from January 2024, you see here spatial temporal return decomposition for multi-agent reinforcement learning. So this is a topic, if you are into robotic, if you are into intelligent flight control, if you understand what we're talking about, this is something that we have to understand, and the research is here simply Yes, you have an idea. So before course, there are years and years of publication and research. So do not be disencouraged if you say, my goodness, this looks so complicated. Start with those three. And if you have those three, then you can come to the main publication. This is DHC. Distributed Heuristic Multi-Agent Pathfinding with Communication. And you see, this already was published in June 2021, a very general paper, but you need to read this paper. You need to understand at least the theory a little bit so you are able to follow along what is happening currently. So I would recommend this then as an additional paper to read here. There is nothing strange or particular happening. We all know what's happening. And I showed you here just one schema from DHC. The three modules, you have the observational encoder, you have the communication block, which you know a multi-head attention, how it is calculated. And then you have here your Q networks communication and. So this is something, if you know how to code, I don't know, the simplest transformer architecture, you are familiar with multi-head attention, how to calculate these convolutional networks, and so on. And if not, no problem. The idea is simple. Look, they have here the idea of a graph convolutional communication process. So communication is one here of the ways for cooperation in our multi-agent system. And 4 or 5 years ago, we had the first publication on this topic. So motivated at the time, we had graph convolution as the latest hot topic for multi-agent communication. And in the work from 2021, they treated here each agent as a node. And a graph then is formalized by connecting here the neighboring nodes, and you immediately get the idea. Two nodes are regarded here as neighbors if they are inside here a particular field of view of each other. You can define this based on time, on energy, on distance, whatever you like. Or if you have different sensor types, you need a LiDAR, you need a radar, you need a visual, you need an infrared. You get the idea. And then graph convolution can be applied here to arrive here to derive communication patterns, and how they calculate it. Yeah, you're not going to believe it, since we are here working here with transformers. They adopt here the multi-head dot product attention mechanism as the convolutional kernel to compute now all the interaction among the agents. So you see, it is putting Lego pieces together. You know in one area how to solve it, and then you combine it with another piece that you discovered, like course, and you drive it together. It's better, it has a better improved functionality, and maybe it's faster, maybe it has a higher quality output. So nobody understands it right from the beginning. There's no central brain that immediately knows everything. It's a trial and error, and hundreds of publications can sometimes lead to nothing, and then one publication that really opens your eyes. Okay, so do not be disencouraged if you do not get it immediately. And as always, there's one sentence to remember, and this is it here. The Q values here in the DHC algorithms are updated using now the modified reward structure, of course. So therefore reflecting both the individual and the cooperative achievements. So this is now, of this latest research publication of AI research, the core idea, integrating the Cooperative Reward Shaping course with the distributed heuristic and communication DHC framework in multi-agent system mass. Beautiful. Okay, you see? Was not that complicated. As I told you, we are operating here in a framework that does not require a centralized planner. So we are operating here in a framework where we can say, like in Amazon in a warehouse, okay, we can let the system run and find its optimal equilibrium of the system. However, there are other systems where you do not have the time. If you travel supersonic, you do not have the time to have here a communication or maybe a voting of your different agent, of your different sensor systems. Hey, should we avoid this going left, right, down, upside, or whatever? But in the case that we have time for the system to learn to interact with its environment, we go for not a centralized planner. Imagine, guided by an individual agent, shortest path DHC innovatively incorporates here all potential short path choices into the model's heuristic input rather than obligating an agent to a specific path. So you see, as I told you, DHC collects data from neighboring agents to inform its decision and employs simply a multi-head attention as a convolutional kernel from 2021 to calculate the interactions among agents. So you see, the interaction also with old theory from graph theory and convolution kernel, it's all coming together if you want to build something. Great. Now, I have given you an oversimplification because if you read the publication by the AI researcher, I've shown you here 2 pages, they really try to solve it here on a mathematical level that we do have a convergence here. Because if you have optimization, and you diverge and you do not come to a common goal, you don't reach it within a predefined time interval, the system does not do its job. So they are now analyzing under what conditions can we achieve here convergence and. So if you want to have a little bit more of a mathematical deep dive, if you like this is the paper for you. Great. So if we have now course and DHC combined, what is the impact? What are the implications of this new system? 2 days old, 3 days old. Behavioral shifts. Agents trained now with this modified Q-learning approach are more apt to avoid selfish actions that could harm now the group dynamics, such as competing for resources, energy, time, specific materials, whatever, or block each other paths. So you want the system to have the perfect equilibrium and not the single agent to reach its individual goal. System-wide optimization. Over time, this leads to an improved global outcome in multiple agent system environments, such as smoother traffic flow, in autonomous vehicle coordination, or a more efficient task distribution in a robotic warehouse, or to avoid simply with multi-sensor underwater obstacles if you go now to a 3-dimensional underwater pathfinding. So in essence, updating here our Q values in the DHC algorithm to reflect both the individual and the cooperative achievement via course fundamentally aligns here the individual agent goal with the collective interest of all the other agents within our system that we are able to calculate to code, and this promotes now a more collaborative and efficient multi-agent ecosystem. I told you it's not that difficult. Okay. Learning. There was a question about how does multi-agent system learn? Now, it is easy in theory. Because either you have a pre-training of each and every LLM in an agent, so you have an optimized agent for itself. And then you say, I do a hybrid approach. So I have a combination of a pre-training and an online learning phase. This is the most effective learning that occurs with this hybrid approach, where agents are initially pre-trained on a data set, on a set of configurations where the AI learns to find here the best solution, the best equilibrium, to learn basic behaviors for our pathfinding, 2-dimensional, 3-dimensional, supersonic, or whatever. And then we have a fine-tuning of the system, of the complete system, through an online learning based on the real-world interaction. If the robot stumbles into the kitchen and tries here to open the fridge, maybe the first 2, 3, 4, 5 times it will fail. But once it learned in the online training here with real-world interaction, the 5th time the robot can open here in this particular environment the fridge with no problems at all. Beautiful. Learning typically involves both understanding here the individual decision making of each agent and how to develop cooperative strategies. So how you implant now this idea of a cooperative goal is not as easy as it sounds here, because as I told you, convergent NNN plus it is in the complexity, the computational complexity, real intense. You need real some computer infrastructure. So unfortunately, I haven't found a way to do this at home, but I think you get the idea. So if you want a simple path forward, this agent might start with a pre-trained model behavior to ensure its basic functionality and its safety operation, and then use, if the system has the time to learn, then use online learning to dynamically adjust to the behavior of other agents and complex environment dynamics. So if we have time that the agent can learn in its environment, this is the way forward. If we have an AI system going supersonic, you do not have the time for this. So you have to predefine here all the different, let's say, possible states of interaction, and you have to take care about possible complexities you will encounter during flight before you start the system. So you see, it all depends here on your specific application, how you want to use this AI system, in what environment you want to use it. And therefore, there's so much research happening now in this particular area, how you bring together all the sensory data from all the different sensors, from all the different agents, from all the different actuators, from all the different pre-calculations or calculations what to do. Imagine you are in a spaceship somewhere on a satellite somewhere around Jupiter. You have a very dense atmosphere where you probe here with your spaceship, and you have to understand here exactly what sensor combination give you now some information on your path forward if you want to dive deeper into the atmosphere of this satellite. So you see, unlimited applications. Very easy example, drones used in delivery services. Again, I think about Amazon. Maybe pre-trained using here simple simulations to understand the basic flight controls and navigation, and then continuously adapt to real-world obstacles and real-world weather conditions through online learning. So you see, if you have the time, beautiful. So whatever we can learn from our drones in our atmosphere here on our planet Earth, great. And then this is the starting point if we want to fly to a different planet or a different satellite with a different, maybe a denser atmosphere. Great. Okay. Now there are some questions about my last video. And I showed you in my last video we were doing a little bit of physics with a network of AI agents. And you notice that I only have one computation agent. I have here, if you want a planning tool, this is our central intelligence, and then I have one computation tool, I have one coding tool, and I have one plot tool. So there is not a lot of complexity hidden. You see, what we can do today, and I think this is really showing you the current edge of AI research with multi-agent, we can do this for one type of agent, one type of tool. But imagine the complexity we would suddenly encounter if we would have limited resources. Imagine we're on a spaceship somewhere on Europa, and you have to calculate something, but you only have a little bit of energy left, but you have 4 AI agents, 4 AI sensor network arrays to compute, to operate, to come to a conclusion for your path downward. So what you do, how you optimize now the interplay of the different sensory networks, of the different AI agent, of the different tools that you have to explore your vicinity in a dense atmosphere. So if you want this not to have here, for example, here with a central intelligence that can think about everything, but if you want to compute this here on a distributed learning platforms where each and every agent, or maybe the most alpha priority agents, have the memory and have the understanding of the environment on where all the other different sensor arrays are and where all the actuators are and the other elements in the network, how to work together. This, to code this and to optimize this is not an easy solution. And this is where we are currently with AI research. Beautiful. So I hope I've given you an overview from the very beginning. How do AI agents learn together, to the latest research paper I can find, just 2-3 days old, on this particular topic. I hope it was interesting. Let's see if there's something else. No, this was the last piece of information. I hope you enjoyed it. I hope you found some new ideas and you see how complex it is to code and try to optimize here a system equilibrium of different AI agents, we are just at the beginning, and MIT is just able to do here one kind of sensor, what kind of agent, and all the optimization steps we have not yet discovered. So if you find this interesting, if you find AI research something that you would like to do in your future, hey, maybe I see you in my next video.